Hello friends, this is my second YouTube tutorial video and the topic of today's discussion is practical application of k-means clustering using Python. This is going to be a practical session and I will not discuss the theoretical concepts of k-means clustering in detail. If you want me to take a session on the theoretical concepts of k-means clustering, please do mention it in the comments. So what is the purpose of k-means clustering? K-means clustering helps us in solving unsupervised learning problems. To give you an example, say a lending company wants to run a marketing campaign on all its customers. Now, obviously, a single marketing campaign will not serve the needs of all the customers. The customers will be varied on the basis of their income, their FICO score, their balance and their credit history, etc. etc. So definitely we need a separate marketing campaign for a group of customers which say has a higher income, higher FICO score and a very good credit history. And of course a marketing campaign will be different as compared to a customer for whom the income is low, their FICO scores maybe are low, etc. etc. So k-means clustering, what it does is on the basis of the data that is available, it segregates the different customers into different smaller groups. So a group of customers will fall in one group and they will have a targeted marketing campaign, and there will be another set of customers in a different group for whom there will be a different set of marketing campaign altogether. So I hope the purpose of k-means clustering is clear. And without wasting any further time, I will get into the practical session. So I will open a Jupyter notebook. In order to save time, I have already written down the code, and all I'll do is copy the code into my notebook and keep on running. So the first part of the code, it's just loading the important libraries. I'm loading matplotlib, I'm loading sklearn and pandas. The dataset that we'll be using is the iris dataset, which is already available in pandas. And I will quickly run the first part, shift and enter. And now I'll have a look at the dataset. So I'll just do this, shift enter. So what this data has is we have the details of 150 flowers. We have the details of their sepal length, sepal width, petal length and petal width all in centimeters. The purpose of this k-means exercise will be to try to separate these flowers into smaller groups. So maybe into 2, 3, 4 groups, whatever seems worthy. We'll try to segregate these flowers into 2 or 3 smaller groups based on the data that we have. That is the sepal length, sepal width, petal length and petal width. So how do we go about segregating this data? The first part obviously is to have a visual representation of this data. So what we will do now is we will do a scatter plot of the sepal length and sepal width. Again, shift enter. Now if we have a look at this, we have the sepal width and the sepal length over here. Clearly it seems like there are two different groups within this data. Now a particular group which has a lower sepal length but a higher sepal width, and there is another group which has a lower sepal width but a higher sepal length. So for example, this set of data over here is very different from the data that we see in the top left corner. There is a top left corner over here and a larger bottom right corner. So definitely the group of flowers are not the same. Not all the flowers are same. There is at least 2 different groups of flowers in the data that we have. Connecting it back to the example that I had given for the lending sector, there may be different types of groups in the lending data as well. But of course over here what we see is 2 different groups of sepal and sepal length and sepal width. Now we will try to run scatter plots of all the 4 variables that we have. So through this Seaborn library, I'll run this. So yes, what we have here is all the different possible scatter plots of the data. Now clearly, if I look into the third diagram in the top row, we have the sepal length versus the petal length, and clearly, at least there are 2 different sorts of flowers in this particular group. One group for which the sepal length is low and also the petal length is low. So this particular graph, it represents the sepal length and the petal length. One group has a lower sepal and petal length, and there is another group which is in the upper right corner, which has a higher sepal length and higher petal length. Definitely, at least we have 2 different varieties of flowers over here. And the 2 different varieties are also visible if you look into other variables. Say for example, in sepal width and petal length, if you see this, there is this segment which has a higher, which is a very low petal length and a higher sepal width, and then this particular segment where the petal length is higher but the sepal width is low. So at least at least there are 2 different clusters which is clearly variable in just the scatter plot itself. Now let us look into some of the data statistic. So I've used the describe command. So okay, so there are 4 variables as we have already discussed, and the count is 150, the total count. We have the means. So the mean sepal length is about 5, the sepal width is about 3, petal length 3, and petal width is about 1. Now, an interesting part of k-means algorithm is that it uses distance. Essentially, it uses the Euclidean distance between various data points. In this case, the data points mean the flowers. So, distance can be impacted by the unit of measurement. Now, even though over here everything is in centimeters, the variability is not the same in the data. And in context of banking data or any other real world problem, there can be a huge amount of variability in the data. And as a result, before doing any kind of k-means work, we need to standardize the data. And that is exactly what we will do in our next step. So from our iris DF data, we will now standardize it. And we have standardized our data. I'll quickly show you the description of the standardized data now. Okay. And as you can see over here, the standard deviations are much lower now. We have standardized our data. So even if there was a lot of variability in the original data, and in this data the variability was still low, in real world problems the variability can be a lot more. And any kind of algorithm like k-means, which uses the distance between variables, the variables need to be standardized so that they are all comparable. Before going any further, I will quickly give you a brief description of how k-means algorithm works. Essentially, what k-means algorithm does is that it initially divides the entire data into random clusters, and through an iterative process we calculate the centroids of all these clusters, and any point which is closest to that particular centroid is assigned to that particular cluster. Now, the first cluster formation, even though it is random, because we keep on iterating it, we keep on assigning points that are closest to the centroid to that particular cluster. With multiple iterations, soon the data is divided into properly visible clusters. This is exactly what is the logic behind the k-means clustering. I will of course not get into the theoretical concepts of detail, but essentially it is a random clustering first, and slowly through iterative process we are able to achieve proper clusters. What is important is for us to know what is the optimal number of clusters. Now, in order to understand the optimal number of clusters, we need to look at the within cluster variance. Now, once we are able to divide our data into smaller clusters, what we would ideally want is that within a particular cluster, the data should be very similar. And across clusters, the two clusters can be very different. 2 or 3 clusters should ideally be very different from each other. But within each of these clusters, the variance should be less. So if we keep on increasing the number of clusters, after a point of time, we will observe that the within cluster sum of squares is not changing. So basically, very soon what will happen is that there will be no extra gain by dividing the data into more clusters. Technically, we can divide the data into 150 clusters in this particular case, in which case each observation will be one different clusters. But then that is not required. The moment the within cluster variance starts to become almost constant, even though the number of clusters are increasing, we should certainly stop. And this particular method is known as the elbow method. So I'll run this part. And clearly what we see here is that initially the within cluster sum of squares was around 600. It reduced to 200 just by taking 2 clusters. It reduced further by 3 clusters. The within cluster sum of squares kept on reducing. We want the within cluster sum of squares to be low. But the thing is that after 3 clusters, the drop with within cluster sum of squares became really low. So certainly we do not need so many clusters. From the concept of for the parsimony, ideally, since the reduction is very low after 3, we will go ahead and stop at 3 clusters for this particular exercise. Because we see that the reduction within sum of clusters after the number of clusters cross 3 is not much. There is definitely a elbow over here. So now, and I will just be using the default variables. So I'll quickly talk about this part where init is equal to kmeans plus plus. Now, as I explained, the first clustering is done in a random manner. K-means plus plus changes it a little bit. In K-means clustering, only the first cluster is done in a random manner. And say if we want to have 3 clusters, the second and third cluster is not done in a random manner. We actually try to see the second cluster is decided in a manner so that the distance between the 2 centroids, the first and the second cluster, is maximum. So the first clustering exercise is not completely random if it is k-means plus plus. The use of this is that it prevents randomization, in a sense that, say for example, just there can be a situation wherein we decide randomly on a set of clusters and someone else comes up with a different set of clusters, and it will result in it can sometimes result in different clustering results. So we do not want our exercise to be biased a lot, and hence this k-means plus plus helps. So only the first cluster is random now, and the second and third cluster are decided on the basis of the distance. So I run this first part, and I also predict the clusters now. So there are 3 clusters that we have built. And in our data also, we now put in the predicted cluster. So this is our scaled data, and I have put in the cluster also now over here. So we have 3 different clusters. The clusters are named as 0, 1 and 2. Now there is something that I did not tell you earlier. this iris data set it actually belongs to three different sets of flowers, and we can Python already has the names of these different sets of flowers. So essentially we did not have to do this clustering exercise over here, because we already know that there are three different flowers in this particular data set. But of course, in real world, we will not know. We will never know like which customer is good or bad in a real world exercise. In this case, we do know. So what I'll do is I'll try and show you that how efficient my clustering is with the actual reality. Now it is to be understood that the actual reality will never be known in many cases. It is one of those cases wherein we already know which flower belongs to which data belongs to which flower, but in most real world unsupervised learning problems, we will never know. The only purpose of this exercise is to understand the accuracy of this particular k-means work. So once I run it, I will quickly show you what I have in the result tab. So after cluster, we now have the target and target name. Target name basically is the actual name of the flower. Now remember, when we did the clustering exercise, we did not know that the data corresponds to three different sets of flowers. We just went about our business without even knowing that this data was each of these data points corresponds to three different sets of flowers. And in real world, essentially, we will never have this particular target name, and hence we are having to do the clustering exercise. But let's see how accurately we have divided our data. So I have run the cross tab of this data, and what we see over here is that our cluster 1, it identifies all of the setosas. So at least the cluster 1 is identifying the setosa accurately. Cluster 0, essentially it identifies the virginica, but even 11 versicolor flowers are also part of this group. And cluster 2 primarily identifies versicolor, but 14 virginica are also part of the second cluster. So while the first cluster is absolutely accurate, there is overlap in this in cluster number 0 and 2, and this can happen. The only reason we know it over here is because we knew the names of the flowers. In real world, we will never know. There in real world, in say for example in customer data, there will never be such a wide variable. So we will never be able to do this kind of a cross tab in real world. We will only be able to segregate the data based on the within cluster sum of squares. But clearly this exercise is working, because in this case we did know, and what we see is that our clustering is pretty much accurate, especially number 1 is pretty much accurate. We have been able to satisfactorily divide our data into 3 different groups. I will now include this spread column in the original data set as well. And let us do a quick visual representation of how the clusters have come up. So I'll use the sepal length and sepal width columns and do a visual representation of our clustering. So over here we can see a visual representation of our clustering, and it is very clear. Now I had done this similar scatter plot earlier also, wherein we did not divide it into clusters. So I'll quickly go in that particular diagram. So this is what we had done, sepal width versus sepal length, and and at that time itself, in the beginning itself, we could see 2 different clusters. The one in the top left corner, and another in the bottom right corner. Now what we have done is that instead of 2, we have divided into 3 different clusters, and I have colored it in yellow, orange, and yellow, orange, and blue. So yellow, orange, and blue, 3 different clusters, and once we look at the data, it becomes pretty clear. At least the yellow part is definitely a different cluster. The blue part is over here, which has a medium range of sepal length and sepal width, and finally a higher sepal length, sepal width part, which is which we have identified as the orange clusters. So 0, 1, 2, 3 different clusters. And in the context of a marketing campaign problem, these will be basically the 3 different set of customers for which 3 different set of marketing campaigns should be run. And finally, I will have a look at how different these clusters are. So I have taken sepal length, sepal width and petal width, and I have taken their minimum, maximum and mean by the clusters, and it is very clearly visible. Say for example, cluster 0, it has a mean, it has the medium, the average sepal length is about 6.7. For cluster 2, the average sepal length is about 5.8, and for cluster 1, the average sepal length is about 5. So clearly 3 different clusters we have, and it is visible in our data also. And using our k-means clustering, we have been able to satisfactorily divide this data into smaller clusters for which any targeted work can be done for each of these separate clusters. So I hope this session was informative for you guys, and I have been able to teach you the practical concept of it and how exactly to run it. If you liked this video, do press the like button and share this video as well. And in case of any feedback, please do mention it in the comments. Thank you.